All right, let's take a look at the 9.3 notes here. 9.2 and 9.3 are very similar. The only thing that's changing is that instead of doing a test about a population proportion, we're now doing a test on a population mean. So the four-step process, you're going to see a lot of similarities, but I want to make sure I point out some of the key differences here. Okay, but we're still doing the four-step process. Like I said, this is going to be your favorite process, as I've been kind of touting it all semester. So the first thing we're going to talk about is the state. Okay, so how the state changes, the only thing that changes is your symbol. Instead of p, you're now looking at mu. You're defining the population mean in the context of the problem. Okay, so now that's the only thing that changes in the state. When we get to the plan, just like when we did confidence intervals, when we're talking about our inference test, we're still talking one sample, but remember when we did confidence intervals for mean, we didn't do a z-score, we did a t-score. So we're doing a t-test here. So we're going to calculate out a t-test here for a population mean. So now T goes with mu. Remember that Z and P go together, T and mu go together. Okay? So now, when we get to the conditions, random, normal, and independent are all the same. However, I apologize, random and independent are exactly the same. Okay? You're still doing normal, but how you get normal is done basically like one of three different ways. Okay? First of all, the easiest way is if the sampling distribution is stated to be normal. Okay? So if this is the case, okay, if it's stated to be normal, then any sampling distribution is normal. The second way is, hey, if it's not stated, is your sample greater than 30? If so, then you get to use the central limit theorem. Okay? However, so I apologize, that's number 2. However, if you have the data when n is less than 30, that's number 3, you're going to have to graph the data and basically show that there's no outliers or strong skewness so that you can assume that it's approximately normal. We a lot of times do this with dot plot, normal probability plots. You can actually do it with histograms, any type of quantitative graphs that help you see what's going on. Okay? All right, so now with the do part, we now calculate out a t statistic. Okay, so now with your t value and your test statistics, same thing here, except it's the standard deviation. Okay, if we take a look at it, in our case, it's going to be this standard deviation, okay, of our sample right there. I apologize. So it is going to be of the statistic, but you're going to take your mean minus the mean of the null divided by the standard deviation of the statistic. So you're going to have to use the sample standard deviation. Now to get your t-score, okay, what you're going to have to do, okay, is instead of using normal CDF, you're going to use this function on your calculator, tCDF. Okay, so tCDF, you're going to type in a lower bound, upper bound, and then you're going to have a value of your degrees of freedom. Okay, remember that degrees of freedom from confidence intervals is n minus 1. Okay, so to get to tCDF on your calculator, you simply go second vars. Okay. And so if I do that on my calculator, second vars, if you look right there, tCDF is, on my calculator, number 6. So even if I'm just going to select it, notice how it's asking you lower, upper degrees of freedom. If you have the old school calculator, remember you just type in lower, comma, upper, comma, and your degrees of freedom. Okay? So that's how we get to it. That's going to get this, again, will help you get your p-value. Okay? So once you have that p-value, your conclusion, 3 steps. Interpret the p-value in the context, determine whether or not you reject or fail to reject. So that's kind of number 2. And then number 3, What do you conclude? Do you conclude the alternative, or you can't conclude the alternative? So you're starting to kind of see kind of a similar pattern as doing these problems throughout. All right, so again, just like in 9.2, have a bunch of examples that I'm going to run through. Okay, so feel free to pause the video anytime you need to get all the stuff down. And plus, I'll probably have a little bit of time just to kind of show you how things are going. All right, so in this first example, number 1, it says every road has one at some point construction zones that have much slower speed limits. Ain't that true in Minnesota here? You know, Minnesota, it's either winter or road construction. So anyway, getting back to the problem, to see if drivers obey these lower speed limits, a police officer used a radar gun to measure the speed miles per hour of a random sample of 10 drivers in a 25-mile-an-hour construction zone. So here are their 10 speeds. The question is, can we conclude that the average speed of the drivers in this construction zone is greater than the posted 25-mile-an-hour speed limit? Okay? So mu is the true mean speed of the drivers in this 25-mile construction zone. We're going to assume that they're going 25 miles an hour. We want to know, is it greater than the posted 25-mile-an-hour speed limit? So everything again there in blue is the state. So we have our null alternative hypothesis, and we've defined mean. Okay? So now, the next step, okay, is our plan. So our plan here, we're going to say what type of test we're going to do. One sample t-test for mean at the 5% significance level. Again, they did give us a significance level, 5% always. So random, yep, we have the police officer took a random sample of 10 drivers. Okay, normal. Now this is where the fun begins. Okay, so since n is 10, we don't know the population is normal, so we need to graph the data. So what I do is I start to look at the data here and I say, all right, my lowest speed looked like it was 21. My highest speed was 33. So I simply, when possible, especially with a small set of data, did a quick dot plot. I started at 20, counted by 2s up to 34. The idea is just to graph each and every dot. So like on the first dot, here's where 27 is, then 33, then 32, then 21, and so forth. So I got 9 of the dots. So as I look at this, I really don't see any outliers. I don't see a point way over here or super high up. I don't see skewness, meaning all the points are here with a couple points going down in that direction. Okay? Since I'm not seeing that, I just want to note our dot plot shows no outliers, maybe just a little skewness, but it's not enough to suggest it's not. So we're going to assume our distribution is approximately normal. The last part is independent, always sampling without replacement. So is our population greater than 10 times our sample? We can definitely say there were at least 100 drivers that go through this construction zone. Okay, so we have that part, good. All right, so now, one of the things you have to do in order to perform the test here is we need to get the sample mean and the sample standard deviation. So as you can see here, I said one variable statistics. So I'm just going to show you this real quick. So I'm just going to go stat edit, and I'm just going to take a minute and type in these scores. So I just go 27, 33, 32, 21, 30 twice, then 29, and 25, 27, and 34. Of course, I'm going to check here because you probably even saw as I was typing it in that it didn't take my 0 there for 30. So I just double check, and I'm just going to double check just to make sure all my numbers are typed in right. Because you type in one number wrong and this screws up everything. All right, so what I do here is I can just go stat, calculate one variable statistics. Whoops, that says list 5. I want it to say list 1. Calculate it out. And there's my sample mean, and there's my sample standard deviation that I'm going to use to calculate out my z-score. Okay, so I noted those values. Degrees of freedom, again, 10 minus 1 is 9. So my t-statistic, my sample mean, minus 25 over my standard deviation gives me a t-score of 3.05. So if I think about my t distribution, which looks like a normal distribution, remember, just not as high and fatter in the tails. So my question is, what is a p-value that is 3.05 standard deviations away from the mean with the degrees of freedom of 9? So that's where TCDF comes into play. So just to show you, second bars, and if I do TCDF, so here I'm going 3.05 to 999 with the degrees of freedom of, whoops, didn't take it down there, 9. Now, honestly, it doesn't matter how many 9s you have in for the upper bound. Okay, so paste that in there, enter, and look at that for my p-value, 0.0069. Okay, so again, we interpret what it means in the context of the problem. So if our null hypothesis is true, so if the mean speed of the drivers in this construction zone was actually 25, what we think it should be, then our results, so our sample of with a mean of 28.8 miles per hour or 1 faster from a sample of 10 cars would only occur 0.69% of the time. So our result is pretty extreme. It's pretty rare that something like we would get a result like this if they were actually going the speed limit. So since our p-value is less than 5%, we're rejecting it, meaning we have statistical evidence, okay, that the average speed of drivers in this construction zone is greater than 25 miles per hour. Okay. So sometimes when you actually do these problems, they might ask you what type of error you might be making. So in this problem, it does ask you, are you making a type 1 error or are you making a type 2 error? So if I think about this, I rejected the null hypothesis. Okay? Well, what if that's a mistake? If I reject the null hypothesis when I shouldn't have, that's a type 1 error. Okay? That means we're saying they're speeding through this intersection when in fact they're not. Okay? That's not good. We might be actually assigning a cop here to patrol an area that actually probably didn't need patrolling in the first place. Cop is taken away from maybe being somewhere where there's much more need. All right, that takes care of the first problem. All right, so the first one was a greater than test. So let's take a look at a less than one. So on this one, a college professor suspects that students at his high school are getting less than 8 hours of sleep a night on average. To test his belief, the professor asks a random sample of 28 students, how much sleep did you get last night? Here is the data in hours. Okay? So the question is, does the data provide convincing evidence to support the professor's suspicion? So the professor thinks that they are not getting the sleep. Okay, so suspects that they are getting less than. So this is our alternative. Okay, we're going to see, is there evidence to conclude this? Hence why I put that in my alternative. I'm going to assume the mean is actually 8. So mean, again, defined in context of the problem, is the actual mean amount of sleep students at the professor's school gets each night on average. Okay? All right, so again, when we get to the plan, okay, so what type of test are we doing? Well, we're doing a one sample. We're doing a t-test. It's for a mean, and it's at 5%. Okay? Is it random? Is it normal? Is it independent? So just like the last one, okay? The professor took a random sample of 28 students. Okay? Is it normal? Well, 28. Why didn't the professor just ask 2 more students? We could have used central limit theorem here, but he didn't. So we have to graph it. I just thought for fun, I would actually graph this by a histogram. You can do a dot plot, but between 2 and less than 4 hours, there's only 2 of them. Between 4 and 6, there is 4, and so forth. So there's my histogram. Histogram looks fairly symmetric, so you can see it's fairly looking like almost like a bell curve. There's no extreme skewness. I didn't get anyone with no sleep or like 20 hours of sleep. Okay, no outliers, no extreme skewness. So I'll assume that it is normal. Independent, we would just want to check just to make sure the population of the school is greater than 10 times the sample. We're going to assume that the school has at least 280 students in it. Okay? So now, for time's sake, I'm not going to type in all 28 of these data points in my calculator, but assuming that I did, what I would do then is do one variable statistics, and I would get my sample mean, 6.643 hours, so that's the average of my 28 students. However, it varies by a little bit under 2 hours, 1.981. Okay. My sample size was 28, which makes my degrees of freedom 27. Okay. So now, calculate out that t-statistic, my sample minus the mean divided by the standard deviation. It gives me a t-score of negative 3.625 standard deviations to the left of the mean. So I'm looking for this tiny little bit of area. Degrees of freedom is 27. Okay? So my p-value, I'm looking at t being less than that t statistic. So t-CDF from negative infinity to its value, degrees of freedom 27. Just to let you know, I'll even try to just show you this one since I take a second to do that. Partially because sometimes this one gives students fits. So if I go negative 99, negative 3.625, and my degrees of freedom is 27. So I'm going to paste that in there and I'm going to hit enter. The reason why I wanted to show you this is students are going to say, wait, Mr. Parts, it says 5.9. It doesn't say 0.0006. Look at what it says here, e to the negative 4. That means I got to move the decimal place over. 1, 2, 3, 4. So it's like saying 0.00059. I rounded to 4 decimal places, hence why it's 0.006. Okay? So again, what does the p-value mean in the context of the problem? If the null hypothesis is true, if the true mean of hours of sleep was 8, then our result, or one more extreme, then our sample result of 0.6641 hours or less from a sample of 28 students would occur our p-value percentage of the time, 0.06% of the time. Since it's less than 5%, oh yeah, we're definitely rejecting this. Meaning we do have statistical evidence or convincing evidence that the true mean hours of sleep at the student or hours of sleep students at the professor's school gets is definitely less than 8 hours. Not very surprised at that result. All right, 2 down, 2 more to go. All right, so now let's click on the next one. One of my favorite problems to talk about because it's a fun children's game that some of us played when we were kids called Don't Break the Ice. So just if you haven't played the game before, or if you have, this might kind of refresh your memory. So in the game Don't Break the Ice, small plastic ice cubes are squeezed into the square frame. Each child takes turn tapping out a cube of ice with a plastic hammer, hoping that the remaining cubes don't collapse. For the game to work correctly, the cubes must be big enough so that they hold each other into place in the plastic frame, but not so big that they're too difficult to tap out. The machine that produces the plastic cubes is designed to make the cubes that are 29.5 millimeters wide, but the actual width does vary a little. Okay? So to ensure that the machine is working well, a supervisor inspects a random sample of 50 cubes every hour and measures their width. The Fathom output below summarizes the data from the sample taken during 1 hour. So what's nice is, here is our sample result. There's our mean, there's our count, there's our standard deviation, and even our standard error. So I'll kind of talk about those as we get to the do part, or the green part of our problem here. So what is our null hypothesis? Well, we're going to assume that, hey, everything's okay. All these ice cubes have a width of 29.5 millimeters. So mu is the true mean width of the plastic ice cubes. The alternative would say, they're not equal to 29.5. Too small, they're not going to be able to hold each other together inside. Too big, you're not going to be able to put them actually in the machine. So they gotta be 29.5. All right, so now, the plan. You'll love the plan when this happens. So again, state the test. 1 sample. It is a t-test because we're talking about a mean, and we're doing it at the 5% level. So, is it random? Absolutely. Supervisors taking a random sample of 50 cubes every hour. Okay. Is it normal? Well, it didn't state it. However, n is 50, which is greater than 30. So according to our central limit theorem, it's okay to assume that our distribution is approximately normal. Okay. So then, is it independent? Well, is our population greater than 10 times our sample? So is our population greater than 500? I think it's safe to assume that this company is making at least 500 ice cubes an hour. Okay? So now what's nice is all of this information right here we're going to use in the do. So I just kind of brought it down and copied it down. So here was our sample mean, here was our sample standard deviation. So thinking about it wise, here, n was 50, degrees of freedom is 49. So I'm going to calculate out my t statistic. So as I calculate that out here, I get a t statistic of negative 0.4597. So visually speaking, my p-value is either negative 0.4597 standard deviations to the left or to the right, too small or too big. Okay? So when I calculate this out, I do one side of it. So for instance, on my calculator, what I can do is second bars again, TCDF, which is number 6. I'm going to do the lower bound, so negative infinity to negative 0.4597. Okay, whoops, my degrees of freedom is 49. I'm going to paste that in there. Voila. Okay, there's my p-value. I need to double this value because it could be on both sides. So my sample result is going to actually occur about 65% of the time. So again, if the true mean of the plastic ice cubes was 29.5, then my sample result from 50 ice cubes or one that's farther away, would occur 64.78% of the time. That's actually very likely. We got a good result. So our p-value, definitely greater than 5%. We're not going to reject the null hypothesis, meaning we do not have convincing evidence to say that the true mean of the plastic ice cubes differs from 29.5. All right, so what's nice is we've done a greater than, a less than, and a not equal to problem. Now the very last problem in just chapter 9 in general, 9.3 here, deals with a special circumstance, a special type of problem that we can do. And it deals with means, and it's doing it where we do it on paired data. If you remember, back in chapter 4, we talked about an experimental design called matched pairs. Okay? If you have an experiment where you're doing matched pairs, you're still going to do a one sample t-test to analyze the data, but what you have to do is subtract your results from each other to see if there's an actual change or a difference between the two things that you're comparing to each other. So to give you an example where you might see something that is a match pairs, okay? Let's take a look at this very last problem. So it says, for their second semester project in AP Stats, Libby and Katie decide to investigate which line was faster at the supermarket, the express lane or the regular lane. To collect data, they randomly select 15 times during the week, went to the same store, bought the same item. However, one of them used the express lane and the other used the regular lane. To decide which lane each of them used, they flipped a coin. They entered their randomly assigned lanes at the same time, and each recorded the time in seconds it took them to complete the transaction. Okay. All right, so let's take a look at this particular data. Of course, if we were doing a problem like this today, I think we would do express lane versus self-checkout lane or something to the extent of that. Okay. So now, if I look at these times, okay, here's the express lane in seconds, regular time or regular lane in seconds. So what I want to do is I want to subtract them. So I got to define how I'm doing the subtraction. This is key because if I define it the other way, then my inequality is the reverse and the alternative, which is okay to do. You just have to be consistent. So I did regular minus express. So I did regular minus express. So in this case, when I did the first one here, I got 5 seconds because 342 minus 337 is a difference of 5 seconds. What that means is the express lane was 5 seconds faster than the regular lane, or the regular lane was 5 seconds slower than the express lane. So I did that for all 15 of my results. So this data right here in orange is what I'm actually going to analyze. So as I write my null and alternative hypothesis, notice how I'm using a subscript here. Mean difference is 0. If they are exactly the same, which I'm thinking there's no difference between the two, then when I would subtract their times, I should get 0. Okay? However, if I think the express lane is faster, this number is going to be smaller, so reg minus express should be a positive number, hence why their difference is greater than for the alternative. Now, if you flip these two, then this value has to be a less than. So make sure we define the mean of D, which is the true mean difference. Notice how I defined it again, regular minus express. If I flip these, then this inequality has to be a greater than. Honestly, in the end, it won't make a difference which way you do it. All that changes is T being positive versus negative. All right, so now I'm going to run through my conditions. Okay? So we're going to perform, in this case, we actually say a matched pairs t-test for the difference or the mean difference at 5%. So random, they actually random times were taken, and which lanes the girls were assigned was also randomly done. Okay, so that's both done. Normal, well, we only did 15. You would think the girls would have done it at least 30 times, but since they did, I actually have to graph the data. So just to show you, I'm actually going to take a minute just to double check this. So if I go to my stat and I go to my edit, I'm going to clear out this data and I'm going to enter in these 15 points. Because some of you might be going, Mr. Carswell, you got 5 and then 246, negative 46. I mean, this is going all over the place. And I couldn't agree with you more. So one of the things I'm just kind of taking my time and trying to enter these in here is, once I get them all in, I'm going to actually do a modified box plot that will show me whether or not outliers actually exist. Okay, so 129, negative 39, and 42. All right, so I'm going to take a minute and just double check because I hate it when I make mistakes, and I make plenty, don't I? All right, so let's see here. That's looking good. So one of the things I'm actually going to do is I'm going to go to my stat plot. I'm going to turn it on. I'm going to go down here and choose the, if it'll let me click over to the modified box plot. I want it on my list 1. So I'm going to go zoom 9 and fit that baby in there. Sorry, I have a y equals equation in there. I'll clear that out and hit the graph again. So if I look at that, that's why down here in my graph, when I graphed it, I did a dot plot, and you might be wondering, this one definitely looks like an outlier. But in fact, look at my box plot, or my modified box plot. Doesn't show an outlier at all. Does have a little bit of skewness, but you know what? It's got to be extreme. So we are still going to assume that it's approximately normal. Okay? So again, the independence piece we want to check. Is the population greater than 10 times the sample? We did 15 times. You know, we're doing an experiment. We could have done this really many more times than 150. So we're good to go there. All right, so now we need to do the calculation. So I'm actually going to the next page. So if you're still writing this, pause it for a second. All right, as I go to the next page, I want to do one variable stats. So what's kind of cool right now is I actually have this in my calculator. So might as well do one variable stats on list 1 and see if my values are matching up. And look at that, they are. Okay? So everything's looking pretty darn good. So now I want to calculate out my t statistic. So my sample mean was 42.67. I'm assuming that it should be 0. What's the probability of getting this result or something bigger if this null hypothesis is true? So I subtract it, calculate out my t-statistic. I get a t-statistic of 1.97. So if I do t-CDF of 1.97, 99 degrees of freedom of 14, my p-value is 0.0345. So So what do I conclude? Well, what does this p-value mean in the context? Well, if the true mean difference of the time was 0, then my sample of 15 with a mean difference of 42.67 seconds or more only occurs 3.45 seconds, or 5% of the time, not seconds, percent, sorry. Again, since our p-value is less than 5%, we do reject the null hypothesis. Therefore, we do have statistical evidence that the express lane is faster on average than our regular lane. All right, this ends our notes for chapter 9.